Okay, this is lecture 6 in linear algebra, and we're at the start of this new chapter, chapter 3 in the text, which is really getting to the center of linear algebra. And I had time to make a first start on it at the end of lecture 5, but now lecture 6 is officially the lecture on vector spaces and subspaces, and then especially there are two subspaces that we're especially interested in. One is the column space of a matrix, the other is the null space of the matrix. So I got to tell you what those are. Okay, so first to remember from lecture 5, what is a vector space? It's a bunch of vectors that where I can add any two vectors in the space, and the answer stays in the space. Or I can multiply any vector in the space by any constant, and the result stays in the space. So that's, in fact, if I combine those two into one, you can see that if I can add and I can multiply by numbers, that really means that I can take linear combinations. So the quick way to say it is that all linear combinations, C, any multiple of V plus any multiple of W, stay in the space. So can I give you examples that are vector spaces and also some examples that are not, to make that point clear? So suppose I'm in 3 dimensions. Then one way to get us one space is the whole 3-dimensional space. So the whole space R3, 3-dimensional space, would be a vector space, because if I have a couple of vectors, I can add them, and I'm certainly okay, and they follow all the rules. So R3 is easy. Now, I'm interested also in subspaces. So there's this key word, subspaces. That's a space, that's some vectors inside the given space, inside R3, that still make up a vector space of their own. It's a vector space inside a vector space. And the simplest example was a plane. So can I just sketch it? There is a plane. It's got to go through the origin, and of course it goes infinitely far. That's a subspace now. Do you see that if I have two vectors on the plane and I add them, the result stays in the plane? If I take a vector in the plane and I multiply by -2, I'm still in the plane. So that plane is a subspace. So let me just make that point. Plane through 0, through that 0, 0, 0, is a subspace. Okay. And also, another subspace would be a line. A line through 0, 0, 0. Yeah, the line has to go through the origin. All subspaces have got to contain the origin, contain the 0 vector. So this line is a subspace. Line is a subspace. Really, if I want to say it really correctly, I should say a subspace of R3. That of R3 was like understood there. Now, so let me call this plane P, and let me call this line L. And let me ask you about other sets of vectors. Suppose I took, so here's the first question. Suppose I take two subspaces, like P and L, and I just put them together, take their union, take all the vectors. So now you've got P and L in mind here. So I have two subspaces. And for example, P, a plane, and L, a line. Okay. Now, I want to ask you about the union of those. So P union L. This is all vectors in P or L or both. Is that a subspace? Is this a subspace? This is or is not a subspace. Because I just want to be sure that I've got the central idea. Suppose I take the vectors in the plane and also the vectors on that line, put them together, so I've got a bunch of vectors. Is it a subspace? Can you give me, like, so the camera can hear it, or maybe it's the tape, can you say yes or no? Do I have a subspace if I take all the vectors on the plane plus all the ones on the line and just join them together? But I'm not taking this guy. Actually, I'm not taking most of them, because most vectors are not on the line or the plane. They're off somewhere else. Do I have a subspace? No. Right, thank you. No. Because. Why not? Because I can't add. Because if that requirement isn't satisfied. If I take one vector like this guy and another vector that happens to come from L and add, I'm off somewhere else. You see that I've gone outside the union. If I just add something from P and something from L, then normally what will happen is I'm outside the union, and I don't have a subspace. So the correct answer is not. Okay, now let me ask you about the other thing we do is take the intersection. So what does intersection mean? Intersection means all vectors that are in both P and L. Is this a subspace? Yeah, so I guess I want to go back up to the same question. This is or is not a subspace. And you can answer the question first for this particular example, this picture I drew. What is P intersect L for this case? It's only 0. At least, sort of, this was the artist's idea as he drew it, that line L was not in the plane and went off somewhere else. And then the only point that was in common was the 0 vector. Is the 0 vector by itself a subspace? Yes, absolutely. And what about if I don't have this plane and this line, but any subspace and any other subspace? So now can I ask that question for any two subspaces? So maybe I'll write it up here. If I'm strong enough. Okay, so this is the general question. I have subspaces, say S and T. And I want to ask you about their intersection. S intersect T, and it is a subspace. Do you see why? Do you see why? If I take the vectors that are in both of the subspaces, so that's like a smaller set of vectors probably, because we've added requirements. It has to be in S and in T. How do I know that's a subspace? Can we just think through that abstract stuff and then I get to the examples? Okay, so why? Suppose I take a couple of vectors that are in the intersection. Why is the sum also in the intersection? Okay, so let me give a name to these vectors. Say V and W. They're in the intersection, so that means they're both in S. also means they're both in T. So what can I say about V plus W? Is it in S? Yes, right? If I take two vectors, V and W, that are both in S, then the sum is in S, because S was a subspace. And if they're both in T, and I add them, then the result is also in T, because T was a subspace. So the result, V plus W, is in the intersection. It's in both, and requirement 1 is satisfied. Requirement 2 is the same. If I take a vector that's in both, I multiply by 7. 7 times that vector is in S, because the vector was in S. 7 times that vector is in T, because the original one was in T. So 7 times that vector is in the intersection. In other words, when you take the intersection of two subspaces, you get probably a smaller subspace, but it is a subspace. Okay. So that's like sort of just emphasizing what these two requirements mean. Again, let me circle those, because those are so important. The sum and the scalar multiplication, which combines into linear combinations. That's what you have to do inside the subspace. Okay, on to the column space. Okay, so my lecture last time started that, and I want to continue it. Okay, column space of a matrix of A. Okay, can I take an example? Say 1, 2, 3, 4. 1, 1, 1, 1. 2, 3, 4, 5. Okay. That's my matrix A. So it's got columns. 3 columns. Those columns are vectors, so the column space of this A, let's stay with this example for a while. The column space of this matrix is a subspace of R what? So what space are we in if I'm looking at the columns of this matrix? R4, right? These are vectors in R4. They're 4-dimensional vectors. So it's this column space of A is a subspace of R4 here, because A is a 4 by 3 matrix. This tells me how many rows there are, how many components in a column, and so we're in R4. Okay, now what's in that subspace? So the column space of A, it's a subspace of R4. I call it the column space of A, like that. So that's my little symbol for some subspace of R4. What's in that subspace? Well, that column certainly is. 1, 2, 3, 4. This column is in, this column is in, and what else? So it's got the columns of A in it, but that's not enough, certainly. Right? I don't have a subspace if I just put in 3 vectors. So how do I fill that out to be a subspace? I take their linear combinations. So the column space of A is all linear combinations of the columns. And that does give me a subspace. It does give me a vector space, because if I have one linear combination and I multiply by 11, I've got another linear combination. If I have a linear combination and I add to another linear combination, I get a third combination. So this is like the smallest space. Like it's got to have those 3 columns in it, and it has to have their combinations, and that's where we stop. Okay, now I'm going to be interested in that space. So like get some idea of what's in that space. How big is that space? Is that space the whole 4-dimensional space? Or is it a subspace inside? Can you, let me just see if you can, I mean, we can get a yes or no answer sometimes without being ready for the complete proof. What do you think? Is the subspace that I'm talking about here, the combinations of those three guys, does that fill the full four-dimensional space? Maybe yes or no on that one? No. No. Somehow our feeling is, and it happens to be right, that if we start with three vectors and take their combinations, we can't get the whole four-dimensional space. Now, so somehow we get a smaller space, but how much smaller? That's okay. That's going to come up here. That's not so immediate. Let me first make this critical connection with linear equations, because behind our abstract definition we have a purpose, and that is to understand AX equal B. So suppose I make the connection. Does AX equal B always have a solution for every B? Have a solution for every right-hand side? I guess that's going to be a yes or no question. And then I'm going to ask which right-hand sides are okay. That's really the question I'm after, is which right-hand sides B do make a... You can see from the way I'm speaking what's the answer to this question, as it is. The answer is no. AX equal B does not have a solution for every B. Why do I say no? Because AX equal B is, it's really, this is four equations and only three unknowns. Right? X is, let me write out that whole, what the whole thing looks like. Yeah. Let me write out AX equal B. AX is, these columns are 1, 2, 3, 4, 1, 1, 1, 1, and 2, 3, 4, 5. Then X, of course, has three components, X1, X2, X3. And I'm trying to hit the right-hand side, B1, B2, B3, and B4. So my first point is I can't always do it. In a way, that just says again what you told me 5 minutes ago, that the combinations of these columns don't fill the whole four-dimensional space. There's going to be some vectors B, a lot of vectors B, that are not combinations of these three columns. Because the combinations of those columns are like going to be just a little plane or something inside R4. Now, so, and you see that I do have four equations and only three unknowns. So, like anybody is going to say, no, you dope, you can't usually solve four equations with only three unknowns. But now I want to say, sometimes you can. For some right-hand sides, I can solve this. So that's the bunch of right-hand sides that I'm interested in right now. Which right-hand sides allow me to solve this? This is the question for today. It's going to have like a nice, clear answer. So my question is, which vectors B allow this system to be solved? And I want to ask you, so that's like, gets 2 question marks to indicate this is the important question. Okay, first, before we give a total answer, give me just a partial answer. Tell me one right-hand side that I know I can solve this thing for. So, all zeros. Okay, that's the, like, guaranteed. If b's were all 0, then I know I can solve it. Let the x's all be 0, no problem. Okay, so that's always okay. Ax equals 0, I can always solve. Now, tell me another right-hand side. Just a specific set of numbers for which I can solve these 4 equations with only 3 unknowns. But if you give me a good right-hand side, I can do it. So tell me one. 1, 2, 3, 4. Can I solve? Is that a good right-hand side? Can you solve? Can you find a solution that x1 plus x2 plus 2x3 is 1, 2x1 plus x2 plus 3x3 is 2, and 2 more equations? So I'm asking you to solve in your head within 5 seconds. 4 equations in 3 unknowns, but you can do it because the right-hand side is like showing up here. It's one of the columns. So tell me what's the x that does solve it. 1, 0, 0. 1, 0, 0 solves it. Because, well, you can multiply this out by rows, but oh God, it's much nicer to say, okay, this is 1 of this column, 0 of this, 0 of this, so it's 1 of that column, which is exactly what we wanted. Okay, so there is a b that's okay. Now tell me another b that's okay, another right-hand side that would be all right. Well, all ones? Actually, and then what's the solution in that case? 0, 1, 0, thanks. And in fact, it's much, like, one way to do it is think of a solution first, right? And then just see what b turns out to be. What b turns out to be, right. Okay. So I think of a solution. So I think of an x. I think of any x1, x2, x3. I do this multiplication, and what have I got? Now I'm ready to answer the big question. I can solve ax equal b exactly when the right-hand side b is a vector in the column space. Good. I can solve ax equal b when b is a combination of the columns, when it's in the column space. So let me write that answer down. I can solve ax equal b exactly when b is in the column space. Let me just say again why that is. Because the column space, by its definition, contains all the combinations. It contains all the AXs. The column space really consists of all vectors A times any X. So those are the B's that I can deal with. If B is a combination of the columns, then that combination tells me what X should be. If B is not a combination of the columns, then there is no X. There's no way to solve AX equal B. Okay. So the column space is really that's really why we're interested in this column space, because it's the central guy. It says when we can solve, and so we got to understand this column space better. let's see. Do I want to think? Yeah, somehow. Oh, well, let's just, as long as we've got it here, what do I get for this particular example? If I take combinations of this and this and this, I'll tell you the question that's in my mind. It's not even proper to use this word yet, but you'll know what it means. Are those three columns independent? If I take the combinations of the three columns, does each column contribute something new? Or not? So that if I take the combinations of those three columns, do I like get some three-dimensional subspace? Do I have three vectors that are like, you know, independent, whatever that means? Or is one of those columns like contributing nothing new, so that actually only two of the columns would have given the same column space? Yeah, that's a good way to ask the question. Finally, I think of it. Can I throw away any columns and have the same column space? Yep. Yes. And which one do you suggest I throw away? 3. Well, 3 is the natural, guy to target. So if and why? Because what's so bad about 3 here? Column 3. It's the sum of these, right? So it's not, if I have combinations of these two and I put in this one, actually, I don't get anything more. So later on, I will call these pivot columns. And the third guy will not be a pivot column in this, with those numbers. Now, actually, but honesty makes me ask you this question. Could I have thrown away column 1? Yes, I could. I could. So when I say pivot columns, my convention is, okay, I'll keep the first ones as long as they're not dependent. So I keep this guy, he's fine, he's aligned. I keep the second guy, it's in a second direction. But the third one, which is in the same plane as the first two, gives me nothing new, it's dependent in the language that we will use, and I don't need it. Okay. So I would describe the column space of this matrix as a two-dimensional subspace of R4. A two-dimensional subspace of R4. Okay. So you're seeing how these vector spaces work, and you're seeing that some idea of dependence or independence is in our future. Okay. Now I want to speak about another vector space, the null space. So again, I'm getting a little ahead because it's in section 3.2, but that's okay. All right, now so I'm ready for the null space. Let me keep the same matrix. And this is going to be a different, totally different subspace. Totally different. Okay. Now, so let me make space for it. Now, here comes a completely different subspace. The null space. Of A. What's in it? It contains not right-hand sides B. It contains x's. It contains all x's that solve this word null is going to, that's the key word here, meaning 0. So this is all solutions x, and of course x's are vectors x1, x2, and x3, to the equation ax equals 0. Well, 4 equations. Because so you see what I'm doing? I'm now saying, okay, columns were great. The column space we understood. Now I'm interested in x's. The only b I'm interested in now is the b of all zeros. The right-hand side is now zeros. And I'm interested in solutions. X's. So where is this null space for this example? These X's have 3 components. So the null space is a subspace. We still have to show it is a subspace of R3. So this is, and we will show. So these vectors X, this is in R3, where the column space was in R4 in our example. For an m by n matrix, this is m, and this is n. Because the number of columns, n, tells me how many unknowns, how many x's multiply those columns. So it tells me the big space, in this case R3, that I'm in. Now, tell me, why don't we figure out what the null space is for this example, just by looking at it. I mean, that's the beauty of small examples, that my official way to find null spaces and column spaces and get all the facts straight would be elimination, and we'll do that. But with a small example, we can see what's going on without going through the mechanics of elimination. So this null space. So I'm talking about, again, the null space. And let me copy again the matrix. 1, 2, 3, 4, 1, 1, 1, 1, and 2, 3, 4, 5. What's in the null space? So I'm taking A times X. So let me write it again. And I want you to solve those 4 equations. In fact, I want you to find all solutions to those 4 equations. Well, actually, first of all, find one. Why should I ask you for all of them? Tell me one solution that you don't even have to look at the matrix to know one solution to this set of equations. It is 0 vector. Whatever that matrix is, its null space contains 0. Because A times the 0 vector sure gives the 0 right-hand side. So the null space certainly contains 0. So it's got a chance to be a vector space now, and it will turn out it is. Okay, tell me another solution. So this particular null space, and of course I'm going to call it n of A for null space, this contains, well, we've already located the 0 vector, and now you're going to tell me another vector that's in the null space, another solution, another x. You see what I'm asking you for is a combination of those columns. That's what I'm always looking at, combinations of columns. But now I'm looking at the x, the weights, the coefficients in the combination. So tell me a good set of numbers to put in there. 1, 1, 1 minus 1. Thanks. 1, 1 minus 1. So there's a vector that's in it. Okay, but have I got a subspace at this point? Certainly not, right? I got just a couple of vectors. There's no way they make a subspace. Tell me, actually, why don't I jump the whole way now? Tell me one more solution. One more x that would work. 2, 2, negative 2. Oh, well, tell me all of them. That would have been easier. Tell me the whole lot now. What is the null space for this matrix? It's all vectors of the form. So what could this be? It could be 1, 1 minus 1. It could be any number c, any number, the same number again, and minus c. In other words, actually, any multiple of this guy. Oh, that's the perfect description, because now the 0 vector is automatically included because C could be 0. The vector I had is included because C could be 1, but now any vector. And that's actually it. And do I have a subspace? And what does it look like? It's in. So how would you describe this? The null space. All these vectors of this form, C, C minus C, like 7, 7, minus 7. Minus 11, plus 11. What have I got here? Describe that whole null space. If I drew it, what do I draw? A line, right? The null space is a line. It's the line through, it's in R3, and the vector 1, 1, negative 1 maybe goes down here. I don't know where it goes, down here. There's the vector 1, 1, negative 1 that you gave me. And where is the vector C, C, negative C? It's on this line. Of course, there's 0, 0, 0 that we had. And what we've got is that whole line going both ways through the origin. The null space is a line in R3. Okay. For that example, we could find all the combinations of the columns that gave 0 at sight. Now, can I just take one more time to go back to the definition of subspace, vector space, and ask you how do I know that the null space is a vector space? How am I entitled to use this word space? I'll never use that word space without meaning that the two requirements are satisfied. Can we just check that they are? So I'm going to check that. Can I just continue here? Check that the solutions to AX equals 0 always give a subspace. And of course the key word is that, space. So what do I have to check? I have to show that if I have one solution, call it X, and another solution, call it X star, that their sum is also a solution, right? That's a requirement. To use that word space, I have to convince myself that if AX is 0, and also an AX star is 0, or maybe I should have said if AV is 0 and AW is 0, then what about V plus W? So let me use those letters. If AV is 0 and AW is 0, then what is it? What's the if that and that, then what's my point here? That A times V plus W must be 0. That says that if V is in the null space and W is in the null space, then their sum V plus W is in the null space. And of course, now that I've written it down, it's totally absurd, ridiculously simple, because matrix multiplication allows me to separate that out into AV plus AW. I shouldn't say absurdly simple. That was a dumb thing to say. We've used here a basic law of matrix multiplication. Actually, we've used it without proving it, but that's okay. We only live so long, and just skip that proof. I think it's called the distributive law, that I can split this into two pieces, but now you see the point, that AV is 0 and AW is 0, so I have 0 plus 0, and I do get 0. It checks. And similarly, I have to show that if AV is 0, then A times any multiple, say 12V, is also 0. And how do I know that? Because I'm allowed to bring that 12 outside. A number, a scalar can move outside, so I have 12 AVs, 12 zeros, I have 0. That checks too. Okay. It's really critical to understand the, oh yeah, what I was going to say, understand what's the point of a vector space. Let me make that point by changing the right-hand side. Oops. Okay, let me change the right-hand side to 1, 2, 3, 4. Oh, okay. Why don't we do all of linear algebra in one lecture? Then we really, okay. I would like to know the solutions to this equation. To those 4 equations. So I have 4 equations. I have only 3 unknowns, so if I don't have a pretty special right-hand side, there won't be any solution at all. But that is a very special right-hand side. And we know that there is a solution. 1, 0, 0. Were there any more solutions? And did they form a vector space? Okay. So I'm asking 2 questions there. One is, so my right-hand side now is not 0 anymore. I'm not looking at the null space because I changed from zeros. So my first question is, do the solutions, if there are any, and there are, do they form a subspace? Let's answer that question first. Yes or no? Do I get a subspace if I look at the solutions to, let me go back to x1, x2, x3. I'm looking at all the x's, at all those vectors in R3 that solve ax equal b. The only thing I've changed is b isn't 0 anymore. Do the x's, the solutions, form a vector space? No, they don't. They absolutely don't. Why? What's an easy way to see that I don't have the solutions to this do not form a subspace. The solutions don't. Because, how shall I see that? The 0 vector is not a solution. So I never even got started. The 0 vector doesn't solve this system. The solutions can't be a vector space. Now, what are they like? Well, we'll see this, but let's do it for this example. So 1, 0, 0 was a solution. You saw that right away. Are there any other solutions? Can you tell me a second solution to this system of equations? 0, negative 1, 1. Boy, that's 0, negative 1, 1. Yes, because that says I take minus this column plus this one, and sure enough, that's right. So there's a bunch of solutions here. But they're not a subspace. I'll tell you what it's like. It's like a plane that doesn't go through the origin, or a line that doesn't go through the origin. Maybe in this case it's a line that doesn't go through the origin if I graph the solutions to ax equal b. So I think you've got the idea. Subspaces have to go through the origin. If I'm looking at x's, then they better solve ax equals 0. In a way, I've got my 2 subspaces that I'm talking about today are kind of the 2 ways I can tell you what about a subspace. If I want to tell you about the column space, I tell you a few columns and I say take their combinations. Like I build up this subspace. I put in a few vectors, their combinations make a subspace. Now when I went to, let me come back to the one that is a subspace here. Here, when I talked about the null space, I didn't tell you what's in it. We had to figure out what was in it. What I told you was the equations that has to be satisfied. You see those? Like those are the two natural ways to tell you what's in a subspace. I can either give you a few vectors and say fill it out, take combinations, or I can give you a system of equations, the requirements that the x's have to satisfy. And both of those ways produce subspaces, and they're the important ways to construct subspaces. Okay, so today's lecture actually got the essentials of 3.2, the idea of the null space. Now we have to tackle, Wednesday, the job of how do we actually get hold of that subspace in an example that's bigger and we can't see it just by eye. Okay, see you Wednesday. Thanks.